Okay, so we are in question number 24 on the Unit 1 practice problem set. In this question, we are given a table and asked, is y a linear function of x? And if so, we want to write a formula for that linear function. So y being a linear function of x, that means the x values are going to be your inputs and the y's are going to be your outputs. What we're looking for this to be linear is that it has a constant rate of change. That's what linear is, okay? So basically that means we need to check the average rate of change from 0 to 5, 5 to 10, 10 to 15, and 15 to 20, and ensure that they are all the same number. And if they're not all the same number, then we don't have a constant rate of change, and therefore it's not linear. Now, the quickest way to do this is to use the delta list function on your calculator and input this value. So row 1 will actually become column 1, and row 2 will become column 2. So I'm going to clear my lists. And before I get too far into this, I want to draw a distinction between number 24, what I'm going to do, and then what I did up here in this problem right up here, which was number 22, I guess. Because I used delta list up here, right? And I used this table, but it's going to be a little bit different, and here's the difference. In number 22, I was given the function, and so for this second column, I didn't have numbers. I had to do y1 of L1, and then that gave me numbers here. And then I moved on to the third column. But in this case, I don't have a function written, I have values. So this is going to be L1, and this is going to be L2. So I don't have to do that y1 of L1 stuff. So it's going to look a little bit different because of that. So L1 will be 0, 5, 10, 15, and 20. Then we'll move to column L2 and we just type in these values. If I can get them down correctly, that's 13.729, 19.904, 26.079, 32.254, and 38.429. Okay, now we go to column 3, and here I still have to go up to L3 and do delta list. So that's second list ops number 7 L2 divide second list ops 7 again second L1. Okay, and notice that we get the same number for every one of them, 1.235. So that means it is linear. So yes. And a formula for this, well, the easiest thing to do is just to do linear regression now. So why don't we just do that? So I'll just go to number 4 under Stat, Calc, LinReg, and hit enter. And so our function will be 1.235x plus 13.729. Okay, so that's number 24. Now, number 25 is similar, but we've got new numbers, so let's see if it holds up. It's still a linear, is it a linear function of x? So we're going to do the same thing and check. But I'm going to have to clear my lists again. Zero, 10, 20, 30, 40. 15.262, 16.043, 16.863, 17.725, 18.632, and that's it. Now we'll check the delta list, column L3, second list, number 7, L2, divide, second list, ops, number 7. I messed up, my bad. I forgot to put in the L1 here, so that's second, L1, and okay. So notice here we do not have the same number. So our average rates of change are not the same, therefore this is not linear. So we're not going to write a formula for the linear function because it's not linear. Okay, great. So let's move on to question 26. This is the last question on the assignment. A country collected $257 billion in taxes in 2015, and its tax revenue is increasing by $22 billion per year. The same country spent $536 billion in 2015, and its expenditures are decreasing by $14 billion per year. Assuming these trends continue, find the first year that the country's budget is balanced, i.e. revenue greater than or equal to expenditures. So this is a little bit more complicated because we actually have two functions to think about. We have a revenue and an expenditure function. And our revenues are increasing and our expenditures are decreasing. So basically, we're looking for that intersection, okay? Now, we're going to need models for each of these. So let's think about how we're going to write down our model. Let's talk about the revenue function. So it collects $257 billion in 2015 and then increases by $22 billion per year. It doesn't specify, and this is going to be a rate. So 22 billion is the rate for the revenue function. This question does not specify whether we need to use the calendar year model or the elapsed time model. So I'm going to use elapsed time. So I'm going to reset the clock. That means I'm going to use mx plus b. So for my revenue model, I'll call it revenue of x is going to be, at time 0, we had 257, and then we're increasing by 22 billion each year, so that's going to be 22x plus 257. For my expenditures, let's call that E of x. And you know, I used x here, but honestly, I really should use t, because that's time. Let's change that to t. Okay, so expenditures at time t. At time 0, we will spend 536, but then we have a decreasing expenditure of 14 billion per year. So since the expenditures are decreasing, that's going to be a negative 14t plus 536. And then we want to know when these two functions intersect one another. So that means that we're going to graph them and do calc intersect. That'll give us an elapsed time, and then we'll have to convert that elapsed time to a calendar year. Actually, I said intersect, but I might just use the table for this. But let's go ahead and get them into the calculator. And let me clear everything. clear this. All right, so my revenue function is 22x plus 257. My expenditure function is minus or negative 14x plus 536. My window, no, actually I said I was going to use the table for this, right? Now why am I going to use the table? Well, first of all, this data is discrete data, so we only have, per year we have one value. So per year we have one revenue and one expenditure. So that means we're going to use this rounding scheme where we always round up. And the easiest way to look at that is just to find the point on the table when we have met or exceeded our value. And let me start my table at time 0. And then we'll go to the table. And we're looking for when revenue exceeds expenditure. So that's going to be for y1 to be larger than y2. So when does y1 get to be larger than y2? So you see here, in year 7 we were at 411 and 438, but in year 8 we're at 433 and 424. So the first year that we exceed is year 8, meet or exceed, and so that's going to be our year, is 8 years thereafter. And using the table, I don't have to worry about rounding. I can just immediately read my answer off. If you use CalcIntersect and you got like 7.3 or something, you would still round that up to 8 in this example. All right, so 8 years after 2015 is 2033. And so that's our answer, 2033. All right, and that concludes the Unit 1 practice problems. Actually, I just said 2033. I said we were done, but I made a mistake here, arithmetic mistake. That is 2023. I'm sorry about that. 2023, not 2033. All right, and now we are done.